Yeah. Okay, that's November 9, 2022. That's 9:17 a.m. Pacific time. So we're covering conservation of momentum. Conservation of momentum. And I'm giving you an example of how momentum is conserved in real life. Here you go. I'm gonna get this axis here. You always, and then I'm gonna get the y-axis as well. Conservation of momentum. Example. Real life example. Okay. Skater. Let me fill that up. Here you go, white. Okay. Real life example. Okay, we're having some heavy rain here. Okay, if there's a chance that the light's gonna go off. If the light goes off, just be patient and wait, and I will come back with my cell phone here. Usually when the light goes off here, it doesn't last very long, it's just 2 or 3 minutes. So don't go away, okay? So here you go. Consider a momentum real life example. Skater spinning around her axis with arm compressed, right? With arm not extended, with arm next to body, next to the body. Here you go. Life example. So if I'm going to, be strictly speaking, yeah, it can be modeled as a cylinder, right? A cylinder with other small cylinders nearby here, but approximately it is a cylinder, right? The skater is approximately a cylinder. The legs, right, there are also 2 cylinders, can be modeled as 2 cylinders. Overall, a very good approximation for a skater, and the head can be modeled approximately as a sphere. Not too big a head, right? Smaller. That's what we do in physics, okay? In order to have a first order estimate, we come up with very simple models of a skater, but this thing can be approximate to that of a cylinder, of a solid cylinder. This geometry can be approximated that of solid cylinder. And here you go, I'm going to denote the angular velocity of the skater. Okay. Insert equation, here you go. Omega, vector, and I'll put it in red color. Okay, that's the angular velocity of my skater next to the body. And then when the skater extends her arm, then it can be modeled as a cross, right? Conservation of momentum, real life example, skate with her arms with her arms around her axis, with arms extended. Okay. So here, the skater has one angular momentum that I'm going to call I naught. Okay. And here the skater has another angular momentum. And also I'm going to put it to omega naught as well for the initial angular velocity, right? And in the next illustration, the skater has this other angular velocity. Okay, with a different angular momentum, IF. And I'll change the color. Here would be the angular momentum of a cross. Okay. With respect, actually it should be angular momentum of a rod, right? A vertical rod plus the angular momentum of a horizontal rod. Do you see that? Here's the same thing, right? The angular momentum of another rod, a cylinder, can be approximated to the angular momentum of a cylinder. And here should be the angular momentum of a vertical cylinder and a horizontal rod or horizontal cylinder as well. Okay, in this case, makes sense. So here we go. Let's do the example, but let me document that first in my notes. Okay, example of angular momentum, of conservation of angular momentum. Skater spinning around her longitudinal axis. When her arms are extended, she has a given angular momentum that is the angular momentum of a solid cylinder rotating around its longitudinal axis, that is that can be, here you go, that can be modeled, that can be approximated, let's put it this way, as a solid cylinder rotating around its longitudinal axis plus a rod, right? Because the arms are much thinner than the body of the skater, right? Plus a horizontal rod. With an axis perpendicular to the length of the rod, right? And here our book already have it. Already have the long, I can say that's a rod because the diameter of the arms is smaller than the diameter of the body, right? So here you go. That's the moment of inertia of the cylinder, and that will be the moment of inertia of your rod rotating about an axis perpendicular to the rod, passing through the center of mass. Okay. Plus the rest of rod with an axis perpendicular to the length rotating about an axis perpendicular to the length of the rod that passes through the rod's center of mass. Okay. Okay, here's a very good moment on, very good model. When her arms are compressed, towards the body. Okay, she has a given angular momentum that can be approximate to that of a solid cylinder. That's all. Okay. Now there is one more thing here that's interesting. I'm going to tell you, okay? Because the moment of inertia is a function of the distances of the points of the object, from the axis of rotation. Okay, we can estimate that the moment of inertia of the skater is larger whenever her arms are extended. Make sense? Okay. Whenever her arms are extended. So see that the axis of rotation is about the center, the longitudinal axis of the body, right? And the distance of the arm is greater here than the distance here, right? The mass of the skater doesn't change, but the mass distribution has changed. Here you go. The mass of the skater does not change, but her mass distribution does change. Okay, for this reason, here's her mass distribution with respect to the position, to its position, right? With respect to its position about the axis of rotation, that's change. For this reason, you know. For this reason, the moment of inertia changes. So we have a situation like that, you know, just like I wrote before. Here you go. The direction of the angular velocity, because the direction of the angular velocity doesn't change, because the direction of the angular velocity does not change, we can simplify the above equation as, you know, I naught omega naught without a vector there at the top. Okay, omega f. So what's happening here? Here we go. We have let's see, when his arm are extended, I should put that at the beginning, right? Here you go. When her arms are compressed toward the body, right? Are close to the body, to her body. she has a given angular momentum that can be made to that a solid cylinder rotate about its longitudinal axis. When his arms are extended, she has an angular momentum that can be approximated as a solid cylinder rotating around its longitudinal axis, plus horizontal rod rotating about an axis perpendicular to the length of the rod, passing through the rod's center of mass, So here you go. So that's the initial position, right? Initial position. Let's put here, initial position. Final position, right? Just like I have in my drawing right here. Initial position, final position, right? So let's take a look again at the right in here. What a shame, it's not going there. Okay. Good. Statistics of the spinning skater. Then they treat it numerically. Let's see if they treat a nice skater is spinning with both arms and legs over outstretched. She pulls her arm and leg inwards. Okay, here they made a the legs also, right? Stretched. Pulls her arm and leg and outstretched. Okay. I made a simpler model, right? My model, the leg is together here. Only the arms are stretched. Okay, neglect any air resistance. Okay. So why neglect any air resistance and assume that friction between these cases? Okay, so here you go. He's asking why is that, right? Do we have a net torque acting on the skater? We don't have a net torque acting on the skater, right? No net external torque acts on her. He's simply obeying the conservation of angular momentum. Due to the movement of her line, net internal torque acts on the skater, causing her angular momentum and omega to decrease. Okay. There is no internal torque. Okay, there's no internal torque. Okay, what actually is happening? It is the energy of the arms that's transferring to the chemical energy of her arms that's transferring to the kinetic and to rotational kinetic energy of the skater. Okay, via conservation of angular momentum. Okay. So with the arm compressed, I is less. With the arm extended, I is more. Okay, so the situation is like that again. Here you go. Remember, I'm considering initially with the arms compressed, right? Here you go. IF with the arm extended is the IF greater than I naught. Okay, because the mass distribution is further away from the axis of rotation. So we can find out what's going to be the final velocity. So here we go. We can pass that to the other side, right? That's what omega F is going to be. Let's see here what's going on. Yeah, that's okay. I gotta put the omega not here. Okay, so we analyze this equation. I'm gonna do even better than that. Instead of I naught, I'm going to put arms closer to the body. Okay, here you go. Arms extended. That's better, right? arms extended. IF is IX. I naught is, okay, arms extended has a moment of inertia greater than the arms contracted. And now I'm going to change it here too. Instead of initial, I'm going to put arms compressed and arms extended, just like the other one. Arms compressed, arms extended. Just changing the notation. Here you go. Now we look at this equation. What we have here is a number that's less than 1 by oh, I'm gonna change it here. Compressed, extended. What we have here is a number that's less than 1 because IX greater than IC, right? What does it imply? It implies that angular velocity with the arms extended is less than angular velocity with the arms compressed. Okay? That's the explanation for that real life situation. We didn't cover that, satellite in elliptical orbit, so you can skip that, right? And we didn't cover that either. Okay, so let's take a look at this one. Rotational kinetic energy. We saw blah, 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 and answer the question. Let's see. At the moment of inertia, I naught and is rotated angular velocity omega naught when she brings her arm. Okay, assume her rotational velocity doubles. Calculate the ratio of her rotational kinetic energy to her initial rotational kinetic energy. Okay, and answer the question. Okay. That's because the angular velocity doubles. Let's do that. Here you go. We saw how it's spinning. But what about her rotational kinetic energy? Is that also conserved? Assume the skater has a moment of inertia I naught and is rotating at angular velocity of omega naught. When she brings her arm in, assume her rotational doubles. Calculate the ratio of her final rotational kinetic energy. Okay, and he didn't give you the moment of inertia IF, right? Well, here you go. That's the ratio, right? So let's do that. What about the ratio? What about given? Here you go. Given IC and IX, given IC and IX, given IC, IX, and IX, and what else? Omega C equal to twice omega S X, right? Just a different notation here. Find the ratio between the, which ratio does he want? The final kinetic energy and the initial kinetic energy. Find the ratio between the final rotational kinetic energy and the initial rotational kinetic energy. That's what he's asking that in that example, right? So here we go. Not initial, right? The ratio between, let's see, the rotational kinetic energy with her arms closer to the body, to her body, right? To her body, and the rotational kinetic energy with her arms extended. Okay. So here we go. So we have rotational kinetic energy extended, right? Arms extended is equal to half. You go, I extended omega extended. Don't forget that the square. That's the rotational kinetic energy with the arms extended. Rotational kinetic energy with the arms compressed. It's something like that. Right? So what they want this divided by this. Right? So here we go. Extended. You go. Like that. Half cancels out with half. Compress this twice the extended angular velocity. Here you go. I'm going to write that down here. Come on, like that. Twice omega compressed, and we get square here. He didn't tell us what's the relation between IC and IX, right? Going back here. Let me see what do they do about the product. Is the oh, that's an interesting way that they did, right? Here you go. Yeah, but let's continue here. Did they use the twice? Yeah, they used it twice. That's good. Okay, so we're gonna get, see here. I omega. Okay, let's see. Oh, I didn't. Yeah. Let me see what I did here. Yeah, well, let's do according to the book, right? Let's remove that, and then we worry about that later on. Here you go. The half cancels out, and then, you know, the book did an interesting trick here, mathematical trick, right? Here you go. The book did something like that. Omega C times omega C, right? And omega X times omega X, right? And now, what else the book did? You know, he recognized that this relation here is conserved. Okay, here you go. Because this is the angular momentum. Angular momentum is the hands compressed. Angular momentum is the hands extended, right? So here you go. We can write that down as being L here and L here. Angular momentum. L cancels with L. And then we use the fact that with the hands compressed, the arms compressed, the angular velocity is twice the angular velocity of the arms extended. And we discover that the rotational energy, kinetic rotational energy, doubles. Okay? That's how we do it. See, the little trick here. Sometimes it's not obvious, right? This little trick. You're just breaking down the I omega F square, I omega naught square. It's 9:47. And we can stop now. Let's have any questions. Let's have our break now, and we'll upload the spreadsheet for the next lab. Let's take a look here what the next lab is. The next lab is Newton's second law. Okay, let's put here chapter 9, right? Chapter 9, lab 5. I will, don't forget, we changed the date of the third exam. I will upload this syllabus to the shareable folder in the Google Drive. Lab report, exam syllabus, syllabi. Okay, 10. And group we go, group physics, shareable folder, lecture notes, confidence level. Good, I can erase that. And I will upload it right now. And I will also, okay, so I will also upload the notes, okay? So bear with me, and no, not this one, that's the lab notes, lecture notes. Okay, reminder, I changed the date of the third exam to be in 2 weeks from now. Okay. Break from 9:50 a.m. to 10:05 a.m. If you don't have any questions, we can go for the break now. Okay, so see you shortly. Download the spreadsheet data for lab 5. I just uploaded there for you. It is, let's see where it is. Group, yeah, right in here. That's for group 9, right? Group 1 is here. Lab 5. Group 2. Let's close this one. Lab 5 and so on. Okay. If you want to take a look at my previous labs, your channel, I have lab 5 there. Let's take a look. Let's see, playlist. Physics lab. Let's see, I don't want to play all, I just want to view full playlist. Oh yeah, here you go, view full playlist. Oh yeah, that's the one. It's only 8 minutes long, right? 8 minutes, 45 seconds. Let's play it quickly. And then if there's anything missing, I'll let you know. October 12, 2021, Tuesday's lab on second block. I'm going to do this quickly. How it's supposed to do. You can see now we are going to use the absolute maximum. 35 using second block motion. We are going to do around this one. Let me pause quickly. Here you go. We changed it too much. Here you go. What we're going to do is an experiment on using what we call the Atwood machine. The Atwood machine looks just like that. It's a pulley with 2 masses connected by a string. Of course, there's a support for this pulley, right? And one mass has a larger mass than the other one. If mass 1 is greater than mass 2, the whole set is going to accelerate in this direction. M1 is going to go down, M2 is going to go up, right? That's the experiment that I'm talking about. We do this experiment over and over again there at the college. It works very well. And let's go. Second block motion. The way I'm going to do it around you just one. By the way, is my voice loud enough? Can you hear all of that, or what I have to increase the volume here? Let me hear from you folks. Okay, before we go into the lab, let me take attendance, right? I'm almost forgetting to take attendance, and then we can go back to that. Yeah. Let's see how I'm going to compress it. To the lab attendance. Today is the 7th, the 9th. Yeah. Vanessa Bonilla, are you there? Okay, thank you, Raymond. Is Vanessa Bonilla there? Okay, I'll try to raise the volume. Thank you, Raymond. So let's see if Vanessa Bonilla is here. Yeah, Vanessa Bonilla is here, but she's not answering. Okay. I'm going to put a star here. Fisher, are you there, Fisher?
Yes, I'm here.
Thank you. Blessing. Are you there, Blessing? Blessing is here, but I don't. It's not answering. Here you go. Janet Garcia, are you there?
Yeah, I'm here.
Okay. Let me raise my volume here so low. Let's see here. Wendy Hernandez. I don't think Wendy is here. Let's go for the next one. Ryan Ong.
I'm here.
Thank you. Mia Villalobos.
Here, Professor.
Thank you. Raymond Garcia. Thank you, Raymond. Joshua Jimenez.
I'm here, Professor.
Thank you. Lily. Thank you, Lily. Michael, yeah, here you go. Thank you, Daisy Mariscal. Daisy, let's see if she's here. I see Daisy here in the list, but she's not answering. All right, thank you, Daisy. Donia? Donia's here as well, right?
Here.
Thank you, Donia. Someone is trying to join us. Ana Lopez. I don't see Ana Lopez here. Next is Mary. Mary just joined us, right, Mary? Let me know you can hear me, Mary. I see her in the list. I'm gonna put a star until she answered again. There you go. Jennifer Perez. Thank you, Jennifer. Elika Vape. I don't see Elika here. Okay. Arthur Pacheco. Thank you, Arthur. Brianna Valencia. Thank you, Brianna. Basilio Lopez. Thank you, Basilio. Bahag, Mard. It was earlier, right, Bahag? Is there in my list? I'm gonna put a star here. Alejandra Marmolejo. I don't see Alejandra in my list, my roster either. Next is Amarilis.
Here.
Thank you, Amarilis. Yesenia Montes Rodriguez. Yesenia here. I don't see Yesenia here in my list. Montes Rodriguez. Let's see. Nope, Yesenia is not here. Okay, so next is Lebilud. Thank you, Lebilud. Lydia Rosas Buenrostro. Lydia, I don't see Lydia either. Justena Youssef. Are you there, Justena? Nope. Okay, one more. Jade.
Here.
Thank you, Jade. Ashley. I don't see Ashley either. Okay, so let's sum everything here. Mhm. 17, let's see here.
Mary's here, Professor.
Okay, let's see. Which group are you, Mary?
7.
7?
Yes, Professor.
I don't see you. Let's see. Were you on group 3 before?
Yes, Professor.
Let's see. Why I can't find it? Let's see here. Okay, key. Oh, okay, here you go. Oh, okay, you were on group 5 before, right?
Yes.
Now you're on group 7, is that right?
Yes, sir.
Okay. So he go Mary. Anybody else? So now we have 18. 18, right? Justana, Yusef, Justana. And let's see, 1, 2, 3. Okay. Justana, Yusef. Are you there, Justana? Looks like he's still logging in. Doesn't look like she managed to log in. Okay, so 1, 2, 3. Okay, so let's you know what? Let me show you the before, instead of showing the video, let me show you the slide, right? The PowerPoint slide. Then you can always review the video there at home, right? This one here, nope, didn't like it. This one maybe. No. Okay, I must have changed places here. Let's see. Let me find this PowerPoint. Lab reports, syllabus. Oh. Let's see, maybe it's here. Lab manual, no. Let's see, no, not this one. Here, illustrations, here you go. Illustrations, lab slides. Be this one. Yeah, Newton's second law, here you go. Good, so here you go. So what's the process here? What's the procedure, right? Well, we have a bunch of equipment there at the college, and we can come up with some very neat experiments. One of them is how to verify Newton's second law of motion, right? And what we do, we suspend a pulley from using a rod, okay? We have a table there too. And then after suspending the pulley, we hang 2 masses through a string. Mass M1 and M2. Notice that we have a support for the mass. The mass that we use are the slotted masses. It comes in small pieces, different masses. And what we do next, we measure the height of one of the masses, the heaviest mass. Okay, mass 1 and mass 2, right? Mass 1 should be almost touching the floor, almost, not completely, but just almost touching the floor. And let's see. So here you go. I'm gonna document as well. Lab notes here. Here you go. And what do? We measure masses 1 and 2 using a scale that has 100 grams, 100th of a gram of resolution. Okay, let's get that here in our. Not this one, is this one here. Here you go. Procedure 1. Suspend a pulley using a rod. Okay. 2. Connect two masses. Let's see here. Let me see what's the best way of. Let's see. Yeah, let's continue here. You got suspend the pulley using a rod. Measure mass 1 and mass 2 using a scale. The scale has a scale with a resolution 0.01 grams, right? Here you go. .01 grams. You're going to end up having 5 decimal places in the kilogram, and you write down your mass in your scale with 5 decimal places in the kilogram. And let me get one of the spreadsheets as well, so you can follow the spreadsheet. Not this guy. I'm gonna get here this last one. Okay, so that's your table that you have for lab number 5, right? Make sure you have 9.8 meters per second square here in this table. And then in mass 1 and mass 2, you're going to have a bunch of values here. It's going to vary from one group to another one, okay? It's not going to be exactly the same value. Let's take a look. M1 here in this case is 0.55263. Okay, that's the mass of the slotted mass plus the mass support. Here, 5/8. So M2 is greater than M1. Okay. So we have, what do we do? We start with those 2 values that you saw, and then, we keep on the net mass of the system, we keep it constant to ensure that M1 plus M2 is the same. So how do we do that? You just exchange masses from the M2 to M1, okay, and to get different accelerations. That's how we do. It's a very nice experiment. Smart. It's a very smart way of performing this experiment. Okay, but let's go with the theory first, right? Here you go. So this mass M2 is suspended at height h. Let's take a look at height h. Here you go, height h. It's approximately 1.5 meters, 1.6 meters. I have seen all the way down, all the way up to 1.7. And we use, in order to measure this height, we use a meter stick. A meter stick has the same resolution of the ruler. So here you go, measure mass 1 and 2. So we do not need that. Measure M1 and M2. So using a scale, M2 is greater than M1. We don't need that anymore. Measure the height of M2 with a meter stick. With a meter stick, resolution, right? Resolution 1 millimeter. Consequently, the value h, measure the height h of M2 to be up to the third decimal place in meters, and use a timer to determine the period of fall of the heaviest mass. The resolution of our timers in our cell phone is hundredths of a second, 0.01 seconds. That's how you log the values, right? Without the second, of course, and repeat that 3 times. So here you go. Data and data, right? And data as well. Here you go. Have height 1.51. Repeat 3 times. Oh, and don't forget the timer, right? Here you go. T1, T2, and T3. So all of that is data. All of that's data. Raw data. Okay. What's the theory behind that? What's the theory behind that? Okay, after determining the time fall, we take the average of those 3 times. Make sure you record the time, the average time with the proper number of significant figures. All of that, remember, is raw data. Here is a result because we're summing M1 with M2. Okay, so let's document that. Here you go. Lab notes. So raw data. M1, M2, H, right? Let me copy M1, M2, H. Let's put that in, with italics. H, T1, T2, T3. T1, T2, T3. And then we have results. Results. The first result that we see in our table is M1 plus M2. The next result that we see in the table, in our tables, is, is going to be the average. We have to transform T1, T2, T3 into T average. Make sure you get the right significant digits there. Then, with the values for T average and the height, we determine the acceleration. So that's another acceleration. Okay. Let's see if I have the equation for the acceleration here. Here you go. That's the equation for the acceleration. How do we get this equation? Well, how do I get this equation? Think about that. The equation here comes from that how do we get this acceleration here? So h over t squared, right? We get that from the kinematics equation, right? Y equal to y naught, right? Plus b naught t plus half a t squared. But don't forget, this t is going to be the average t. Okay. Now, what's next? Y is the final position. The final position is 0. The initial position, why not, is h. The initial velocity, you release your masses from rest. And then you end up with something like that. Right? Let's see here. And let me see here. In the final position. Let's take a look here at the, it's like that, the axis is upwards. Okay, yeah. So we solve that for A. We pass the H to the other side, becomes a negative. Okay. And then we solve for A to H over T average square. That's where that comes from, okay? And this negative means that the acceleration is downwards. That's all it means. I'm just taking the magnitude of the acceleration. That's all I'm doing. Okay, I'm just taking the magnitude of the acceleration. We don't need this negative sign here. Okay. The negative acceleration means that my axis is upwards, right? And my acceleration is downwards. That's what it means. That's why we got the negative here. So what else? Results. We have more results here. And then we have a difference in masses. We need that, M2 minus M1. Okay, and then we have the net force too. So let's take a look how the theory, I didn't cover about the theory, okay? And we have this net force as well, okay? The theory is like that. Okay, so here go. That's my system, right? System of two masses. And we have the weight of 2 pulling down and the weight of 1 pulling down as well. The net force is going to be weight of 2 minus weight of 1. Okay, we go. Theory. Oh, I have it here. I have already spelled out for you. Here you go, theory. Net force is M2G minus M1G. Net force is mass times acceleration, where mass is the net mass of my system. That's why I put M2 plus M1 times the acceleration. Okay. Here, one way to get the acceleration. Here's another way of getting the acceleration. Okay, this acceleration here is obtained using kinematics. Kinematics. Okay. And what else? What's next? Now we are going to have this equation here on the left side, M2 minus M1G. I need this M2 minus M1, okay? M2 plus M1A. Okay, net force change, acceleration change. What does not change is M1 plus M2, because why is that? Because we are keeping this mass constant. Well, whatever little slotted mass that we have here, we repeat the experiment with one value of M1 and another value of M2, right? And then repeat the experiment with another value of M1 and M2, but keep it constant. Okay? So the way let me just illustrate it too, so you have a better understanding how is that, okay? Here you go. Here you go. Here my support for the slotted mass, okay? So we have one is lot mass, another is slotted mass here, and send to back. Okay, here you go. Another slotted mass here, another slot mass here. Here's the support. And let's say this one is M2, which is the heaviest one. Send to back. Okay. I'm going to even put it in a separate slide so you don't get it too busy here. Okay, here you go. I'm going to put, let's say this one is M2. Everything else move it here. Okay, and M1 is going to be, let me put more slotted masses here, otherwise we're going to run out of space, right? So here you go. Here you go. So we have this bunch of slotted masses that we put it in the support, send to back. That's M1, that's M2, and this one is M1. Okay, we have more mass 2 than more than on 1, so the system will be accelerated in the direction of M1, M2. So we run the experiment once. Okay, we run the experiment once, and that's what we have in the first row right here. Note that we have 0.55263, 0.5869, M2 greater than M1. Right? I'm going to invert here the order. So we have it in the proper order. Here you go. First run. Here you go. First run. Get T1, T2, T3, right? First run. Then what do you do? In order to keep the net mass constant, what do? We get one of those little slotted masses here and place on M1 and run the experiment again. The net force here is going to be different from the net force here, right? The net force here is going to be less than the net force here. Make sense? Okay, but we keep the M1 plus M2 constant. Then we go for a third run. For the third run, we place another slot mass on the other side to change the net force again. We do that 6 times. That's what we're doing right in here. Okay, that's what we're doing right in here. We're just exchanging mass from M2 to M1 and getting different accelerations and different intervals of time as well. Okay, and the M1 plus M2 are going to remain constant, almost constant, depends how you perform the experiment. Okay, and by virtue of this equation here, by virtue of this equation here, we have net force, which is net mass times acceleration. Net force is going to change, acceleration is going to change, net mass is going to remain the same. So when you plot M2 minus M1G along the y-axis and A along the x-axis, you get a straight line with a slope equal to M2 plus M1. Okay, so that's what you have to do, you know, for this experiment. Plot, you know, M2 along M2 minus M1 along the times G, right? One, plot M2 minus M1 G along the end, A along the x-axis. That's the first thing you do. Let's do that. So that's the theory behind. Okay. We are calculating the A from actual experimental values using kinematics. And we are going to see that this equation here, you know, fits pretty well Newton's law. So let's see how you're doing there. Do I have any questions? Let's see if I have anything else here to share with you. Start with, yeah. So here's all the instructions, right? By exchanging masses between M1 and M2. That's how it's done. Let's see how you folks are doing there. I'm going to plot. Vanessa, are you there, Vanessa? Looks like Vanessa is away. Okay, I'm gonna put here question mark. So I want to know if you download the spreadsheet. Fisher, did you download the spreadsheet, Fisher?
No, sir, still working on it.
You download the spreadsheet, right? First, I want to know if you download the spreadsheet. Okay, let's.
Oh, I've been able to download it, yes.
Oh, you have been. Okay, good. Let's start, right? Yes. Now,
This is
what
lab
about
number 5, correct?
Huh?
This is lab number 5, correct?
Yeah, that's lab number 5.
Okay, it's downloaded, yes.
Yeah. And by the way, if you need, I'm gonna give you a break for lab number 4, okay? Since I didn't correct number 2 and lab number 2 and 3. Well, every time that I fall a little behind with the other lab, I give you a little bit more of time for the other labs, okay? So you can turn, let's put here at the top. Report for lab 4 is postponed, is due next week, okay? Let's do it this way here. Let's do next week. Okay, since I didn't correct lab 2 and 3 yet, you know, I usually give a little bit more of time for the other lab. So if you want to, you know, to tweak a little bit your report for lab number 4, you can do that, okay? So let's go for another one. Blessing, are you there, Blessing? So it looks like Fisher is alone today, right? Are you working with Blessing there, Fisher?
No.
No, okay. So you're working alone, right? Vanessa is not answering, and Blessing is not answering either. Okay, so let's go for the next one. Janet, are you there, Janet? Janet left, huh? I don't see her here anymore. Okay, I'm gonna put a star here for Janet. She's no longer here. Wendy is not here, right? Wendy is not here. Put a question mark here for Wendy, not here. What about Ryan? Are you there, Ryan?
Yes, I'm here.
Okay, did you download the spreadsheet?
Yes.
Okay, do you know the whereabouts of Janet and Wendy? Okay, so are you working together with Mia, Ryan?
Yeah.
Okay,
I
good.
think Jan is here, but I don't know where. I don't know.
Yeah, she didn't answer. Let me see. Janet was here, but she's no longer in my list here. Okay. So Mia, are you there, Mia? Do you download the spreadsheet?
Yes, I did.
Okay, so you're working with Ryan, right?
Yes.
Okay, good. So Raymond, you download the spreadsheet, Raymond? Yeah, good. Thank you. Let me do something else here. Let's see, I'm going to sort. Group number, good. What's going on here today is the 9th. Okay, concentrate on that. Okay, next in line here is Joshua. Are you there, Joshua?
Yeah, I'm here, Professor.
Okay, you're working with Raymond, is that right?
Yeah, we already have the spreadsheet downloaded.
Okay, did you download already or still
Yeah.
downloading it?
Yeah, I already
You
downloaded it already.
Okay, so now you're gonna plot the graph, right?
Yes, sir.
Okay, thank you.
Mhm.
Lily, did you download the spreadsheet? Okay, thank you. And next step now is to plot the graph, okay? So next here, Michael, did you download the spreadsheet, Michael? Okay, good. So next step is to plot the graph, okay? Okay, next here's Daisy.
Yes.
Okay, Daisy Mariscal, are you there?
Yeah.
Okay, do you download the spreadsheet?
Yeah.
Okay, good. So let me know whenever you plot the graph, okay? Donia? Are you there, Donia? Okay, I don't hear from Donia. So Ana Lopez. Ana Lopez is not here. Next is Jennifer Perez, group 6. Okay, do you download the spreadsheet, Jennifer? Yes. Okay, good. Did you plot the graph already? Did you plot the graph already, Jennifer? Okay, I'm going to assume that you didn't plot the graph yet. Alika is not here, right? No. Sorry for my Wi-Fi. Yeah. Okay, so you're ahead of me and Donia. Hang in there. Here you go. Here we go. Let's get this thing here. Good. So you already got, let's see, Arthur Pacheco. Okay, downloaded, have not plotted yet. Okay, thank you. And Brianna Valencia. The spreadsheet still working on the graph. Thank you, Brianna. Mary Okiki. Okay, so you got the slope, right? That's my group, so it was 0.262, right? If I
Yeah,
somehow
Professor, I'm here. Mary's here.
Okay, thank you, Mary. Let's see. Did you download the spreadsheet, Mary?
Yes.
It's only okay, thank you, Donia. And you said that, Donia, you said your group got a slope of 0.262, is that right? Okay, I'll get back to you. Let me, your group number 4, we're gonna plot this graph together. This slope seems a little bit low for me, okay? Let me see what's going on there. Okay, let me see. And Basilio? Okay, okay. Did you plot the graph already, Basilio? Okay, Fisher got 1.2. Okay, I'll get to you, Fisher. Hang in there. Let me check everybody, okay? Okay, you also have been able to plot. Okay, download, plot. So, Basilio. Yes and yes. Let's put it this way. I'll get back to you. Vahag, are you there, Vahag? Yeah, Vahag is mute. Okay, so put here is Alejandra. Alejandra is not there, right? Alejandra Marmolete. So Amarilis, did you download the spreadsheet, Amarilis?
Not yet.
Not yet. Oh, okay. Go ahead. Make sure you download it and okay, so you can catch up with all of us. Okay. So here
Okay.
you go. Labelut, did you download the spreadsheet? See, Janet. I don't hear from you, Labelut.
Oh, yes, I downloaded the spreadsheet, yes.
Yeah, you did download. Did you plot the graph already too?
No, I'm working.
Okay, good. Thank you. Lydia. Lydia is not here, right? I don't see Lydia. And what about Justena? Justena, it looks like Justena's having problems. Okay, here you go, Justena. Are you there? I can't hear from you. Justena. Okay, good. Good. Did you download the graph, the spreadsheet, Justena? Okay, please download this as soon as possible so you can move forward. And here, okay, I'll get to you, Janet. Hang in there, Janet. What's your group, Janet? Group 2. Let's see, group 2, Janet. Okay, okay, good. I'm gonna put attendance here for you. Did you download the spreadsheet, Janet? Yeah, Janet Garcia. Yes, okay. Did you plot the graph already too? Yes? Okay, good. I'll get to you. So let's continue with the other students. Jade, group number 9. Are you there? Okay. Okay, good. It looks like you're working alone, right, Jade? Okay, you're still working on the graph. Okay. And Ashley, Ashley's there. Ashley, I don't see Ashley here. Okay. So let's go from the beginning again. Vanessa, one more chance, Vanessa. I see your name here, but I don't hear it from you. Ah, okay, here you go. You download the spreadsheet, Vanessa? Okay, did you plot the graph? Not yet. Okay, good. So I'll get to you. Hang in there. Fisher, you download the spreadsheet. Did you plot the graph, Fisher?
Yes, I got a slope of 1.2.
1.2. Okay, I'll check that. Let's move to the other students. 1.2. Huh. Okay, so yeah, that's should be. And how much percent are you getting? Oops, what's going on here? What's going on here? Something wrong here. Okay, good. Okay. Well, I'll get to you. What about Blessing? Blessing, are you there, Blessing? I can see Blessing here in my list, but okay, so I'm gonna put another question mark here. Okay, here you go. Next
Professor, the
one.
percentage. Sorry,
that
Professor.
Blessing?
No, this is Fisher.
Okay.
The
So
percentage
what-
difference that I got was 5.87.
5.87. So it's pretty good, right? It's pretty good. Less than anything less than 10% is a good number. Remember, this slope should be close to M1 plus M2, right? There was a group that told me that they got like 0.2 as the slope, right? So that's why I think it's too low. It should be, around 1.1, 1.2. Okay, we're gonna get there. Janet. Okay, I talked to Janet already, right? Let's see. Wendy's not here. Ryan, did you plot the graph, Ryan?
Yes, I did.
Okay, what's the slope are you getting?
I got a slope of 1.301.
Okay, good. 1.3. And the percentage difference should be very small, right? What are you getting for the percentage difference? Oh,
I got like 14.9.
14? 1 4.
Yeah, 14.9.
Okay. 14. I'll check that why you're getting such a high percentage difference. 14 is acceptable, but anything that's below 10%, I don't worry. When you start to get above 10%, I worry a little bit. And if it's above 20%, I worry a lot, 20%, 30% different. I worry. It's kind of there in the 14.5 is kind of there in the range of worry and not worry, anywhere in between. Mia, did you plot the graph, Mia?
I'm still working on it, Professor.
Okay, still working. Okay, good. So let's go. Next is Raymond. Did you plot the graph, Raymond? Still on it? Okay. Okay, I'm gonna put in here. Good. Joshua, did you plot the graph?
No, me and Raymond, we're currently working on it right now. We have
Okay. Okay. No pressure. Wonderful, thank you. Okay, thank you, Lily. Okay, Michael, did you plot the graph, Michael? Still working? Okay, good. Okay, so let's see, Daisy. Slope, okay, here you go. Yeah, 0.937. How much percent difference is that, Daisy? So 18%. Okay, I'll look into our data very soon. Donia, did you plot the graph, Donia? Same answer. Okay, same answer. Okay, good. Should be right because you all have the same data. Okay, Anna is not here. Jennifer, did you plot the graph, Jennifer? Yes. Okay, good. Did you get the slope? What's the slope that you got? .28. And what's the percentage difference? Okay, good. So it's just a matter of putting the slope there in the proper place, right? So let's go here to your, once you plot the graph, you log the slope right here in this last table. And then you know what's the percentage difference right in here. Okay. Now, percentage slope, percentage difference. Next, Artur Pacheco. Did you plot the graph, Artur? Are you there, Artur? Okay, I'm gonna put a question mark here. Next, Brianna Valencia. Did you plot the graph, Brianna? Yes, okay. Which slope did you get? .12. Okay, what's the percentage difference that you're getting? %. Okay. Okay, so Pacheco, right? Arthur Pacheco. Let's see. 1.2. Okay, Arthur Pacheco. Let me see. You're in the same group as Brianna, okay? Okay, good. Okay. So if you got 1.12, so that seems right. Okay. Good, thank you. Will now Mary Okeke. Did you plot the graph, Mary?
Not yet, Professor.
Not yet. Okay. Okay, Basilio, you got this slope, right, Basilio? You got the graph and you got the slope, right? Yes. What was the slope you got? .86, huh? That sounds a little bit too much, too little. But what's the percentage difference you're getting? Let's see what's the percentage difference first. That's not the percentage difference. Is that 0.15% difference? That doesn't sound the right percentage difference. No, it's not the R square. I don't want the R square. I want the percentage difference. Okay, the percentage difference you get right here in this cell whenever you type the slope here on table 4.5, the last table. Okay, did you do that? Okay, so here goes. Oh, yeah, that's right. You type the slope here, and then once you type the slope here, you're supposed to get the percentage difference. Okay, so I'm gonna put a question mark here for the slope, and then I'm gonna put n, right, that you didn't get the percentage difference yet, and then in the next round I ask you again. Okay. 23%. Okay, 23%. Yeah, this one is a little bit high, right? So now what about Fahad? What happened to Fahad? Are you there, Fahad? Okay, I don't see Fahad here. Alejandra Marmolejo is not here. Yeah. Next is Amarilis. Did you download the spreadsheet, Amarilis?
Yeah.
Yes. Okay, good. Did you plot the graph?
I'm still on that.
Okay, good. It's okay that you didn't plot it. We still have time. 11:10, right? You need a break here. Yesenia, are you there, Yesenia? I don't see Yesenia here. Nope. Let's go for Leibelud. Leibelud, did you plot the graph? Good. You plotted. You got the slope 1.3 and percentage difference 17%. Okay. Good. So now go ahead and, if you got the slope, go ahead and do the other things, right? The other things are the units, the significant figures, the CL, and so on, right? That's the most important part of the experiment, is to plot the graph, get the slope compared to what we expect the slope to be. Okay, when you're doing actual research, okay, when you're doing actual research, you are at loss whether your results are are correct or not, because you're doing something brand new, right? That nobody has ever done. So what we do here, we're just practicing for your future research, right? Today we're dealing with well-known experiments that has been performed over and over again with theories that we know are established. We use this type of theory to plot the path of the spacecraft in space. You know, we use all that stuff to send the man to space, man to the moon, spacecraft to other planets, and so on, right? That's the beginning of everything. But when you're doing actual, research, when you're dealing with something that nobody else has ever worked on, you're going to do the same thing. You're going to plot your graphs. You're going to try to find relations, hidden relations, but you're not going to say, you will not know whether your results are correct or not, okay? You will not know. You only gain confidence that your results are correct by performing those experiments that we are performing right now. Justena, are you there, Justena? Justena disappeared. Huh? Okay, I'm going to put a star here on Justena. Question mark. Jade, you plot the graph, Jade? Still working on that. Okay, good. So I see that your group has only 2 students, Jade, right? Only you and Ashley. So if you want to join another group, we have this other group that has only 2 students too, right? Might be helpful. The other group that has 2 students is group 3. Think there if you folks wanna, merge with group 3 or group, and similarly group 3, think if you want to merge with group 9, right? So you have a larger group to do you don't have to do that. You don't have to follow what I'm telling you, but just a suggestion, okay? And now let me help you out. Let's see. Group number 1. What's that? That's not what I want. Raw data. Why raw data? Something wrong here. Doesn't make any sense. Huh. Huh. Ah, okay, it's not supposed to be here. Okay, I'm putting this thing here in the wrong place. Where is it? It's here. I don't have a clue. Oh. No. Okay. Lab 5. Okay. This one's not supposed to be here. Let's see what's going on here. Okay. Lab report. Okay. Okay, good. So lab report, raw data lab. Okay. Lab 5. Lab 14. Bear with me. 11, 14. Yeah, okay, good. I had one of those files in the wrong place. So now let's go get it, raw data. Right? Seems not supposed to be here. Okay. So let's go lab 5 right in here. And so, okay, group 1, Fisher, I'm gonna plot your graph here. Okay, so what do we have to plot? We have to plot the net force and the acceleration, right? Net force and acceleration. And insert, yeah, it's a little bit scattered, right? So you can adjust here the maximum and minimum, right? So you don't have this huge blank space here, but let's take a look at the trend line. Display equation on chart. Yeah, 1.2, right? 1.2, and that's what you got, right, Fisher?
Yeah, that is what I got.
1.2. Yeah, good. So, and then let's take a look at M1 plus M2, right? M1 plus M2 is here. Well, I cannot look at it. Okay, the expected value should be 1.13. You got 1.2, right? Which is pretty good. 1.2, 5%, just like you told me. Okay. Okay, here you go. So I clean that up. Let's go to the next one. So now work on the units and the significant digits. Don't forget you have to worry about 3 significant digits here as well. That's easy, right? Significant digits here as well. Treat the G as though it has an infinite number of significant digits. That's how you should treat the G. Now, next one. I work at this group 1. Let's say group number 2. Let's take a look at the results of group number 2, right? You're getting 15% difference, right? Group number 2. That's what you plot, and that's what you plot. Insert. Yeah, there you go. Get the trend line. Display equation on chart. 1.3. Is that what you got? 1.3. Yeah, 1.3. Okay, M1 plus M2. 0.55 plus 0.58. Is 1.03, right? 1.03, you got 1.3. 1.3. 14%, 0.8, is that what you got? 14.8. Yeah, almost the same, yeah. Good, that's group number 2. Let's take a look at group number 3. Okay, group number 3. Did you plot the graph, Raymond? Raymond and Joshua.
We're currently figuring out. We're just having a little bit of technical difficulties. Sorry about that.
Okay, I'll get back to you later on. Group number 4. So group number 4 already has a result here. Let's take a look at the graph for group number 4. 18% difference, right? Group number 4. Here you go. Net force acceleration. Wow, we have a big gap here. Those students didn't do a good job when they choose what masses to plot, right? It's not a good thing when you're performing experiments to keep it like this huge gap. Okay, it's not a good thing. But let's see. Let's take a look at the trend line. Yeah, okay, it seems to me that this data point here is an outlier. Okay, that's what it looks like to me. That's why the slope is going down. That's group number 4, and that's why you're getting 18% difference. Let me see if we can get a better slope. If I eliminate this data point, I'm gonna get a better slope, okay? And let's see, must be this data point right in here. That's my assumption. Yeah, it's the highest net force and the highest, no, is the highest acceleration. Yeah, so let's eliminate that. No, looks like it's this one here. Let me see. Uh, 3 minus 2. Oh, it's -1. Okay, okay. So which one should be? You know, either one here, because it's 3 to -1. Okay, it's either one or the other. Let's see which one is that. I do not know which one that is. I'm gonna plot, insert. Nope. Okay, here you go. A and this one. So I'm gonna eliminate one of those 2 points. Okay, here you go. Let me eliminate the first one first, and let's see if we get a better result. Let's see. No, I chose the wrong one. I chose the wrong one. That's not the one. That I'm going to eliminate this other one. Oops, not here. This one, this one, this one, and this one. Here you go. Insert. Okay, now let's take a look at the slope now. The slope now is 1.005 by eliminating that outlier. And if I put 1.005, what do I get? 0.05. 12%, not much of a help, but it went down from 18% to 12%, right? So if you were performing this experiment in the lab with me, I would ask you to repeat the experiment for this specific point, okay? Which would be measurement 5 right here. Okay, you got 1.3, Lily. Let me check your group. Let's see your group number. Okay, so let me see. So you did plot the graph. Tell me what's the slope you got, please, Lily. No, the slope. It's 13%, not 1.3. Okay, good. What's the slope that you got, please, Lily? Oh, still doing? Okay, but okay, I'll get back to you once you have it. Let me know. Next, group number 6, right? So Jennifer, did you get 1.28 for your slope or just different than that? I did that, Jennifer. Yeah. So you're group number 6, right? Okay. Yeah. It should be the same, right? It should be 1.12, right? So can I? Yeah. Okay, good. So let's just group number 6. Let's plot that. Insert. Okay, now display 1.12, yeah? I'll say 1.13 because you have 1.1286, right? You round it up. And 1.13, let's put 1.13%. Oh, wow, 0% difference, huh? 1.1286, right? Now should be less. 0.12% difference. That's what I'm getting. 1.12, yeah. So here we go. Okay, so it's not 12%, right? It's not 12% difference, it's 0.12% difference. Let me see if yeah, multiply by 100. So yeah. Okay, so fix that for me. Okay, it's not 12%, it's 0.12% difference. It's very small. It's very small percentage difference. That's for group number 6. Group number 7 is 11:30 already. Let's see, group number 7. I'm gonna plot Vahag. Are you there, Vahag? Looks like Vahag walked away. Oh, here you go. Okay, Vahag, looks like you were away, huh? Did you plot the graph? I'm gonna give you attendance here, working on it right now. Yeah. Okay, so let's see what's the deal here with group number 7, with the graph of group number 7. You're getting a high percentage difference, right? So here you go, plot that, insert. Oh yeah, that's why you're getting a high percentage difference. You have several outliers there, more than one apparently. Maybe those are the outliers, maybe those two are the outliers, I suspect. Okay. Let's see. -1, minus, let's see. That's in the x-axis, -2. It looks like the outliers are those two. That's what it looks like. Okay. Let's see what's the slope we get. 0.86, yeah. Just like you got. Yeah. Now I'm going to eliminate the outliers, okay? And let's see if we get a better slope. Looks like the outliers are those two here. 1.4. Now we're getting a high. 1.4547. Let's see here. 1.4547. 0.4547. 28%. Still 28%. Let's see. Maybe the outlier is. Let's put it back here. Okay, I wonder which ones. Maybe the outlier is this one, this two. Yeah, maybe the outlier is these two here. Okay, so let's see. No, 0.8. Maybe the outlier are those two here. Let's see. Let's see if we can get a better result now. Insert. Trend line. Oh, ay. I did something I was not supposed to do. Yeah. Group 7. Yeah, here you go. Good one. Yeah, it doesn't help. Yeah. Yeah, okay. I do not know what's happening here. Sometimes we get, if I were to do the experiment, maybe the outliers are those 3, maybe those are the outliers here. If I were to do the experiment, I would repeat those 3 here. It's possible that the outliers are those 3, all those 3. 4, 6, and 8. Yeah. 4, 7, and 8. Yeah, it looks like the outliers are all those. Let's see if we get a better result now. Yeah, now we are getting 1.2, right? But now we have so few points, data points. When we reduce the number of data points, you start to question the validity of your data. But it looks like the problem was those 3 data points. Okay, looks like the problem was right in here, those 3 data points. But okay, so no, don't leave it. Don't leave it. Just plot all those 6 there. Okay, don't worry about that. You're not going to be penalized for that. But this is what we did about about discussing about those outliers is a good exercise for future reference. Okay, but again, Basilio, you keep all the points in there. Okay, don't delete them. Now let's see who else. 1132. That's group 7, right? Group 8. Good. Justena, are you there, Justena? No, Justena not there. Okay. And Labelud, right? Let's take a look at you're getting 17%, Labelud. Let's take a look at your graph. Group 8. Group 8. Group 8, 8, 8, 8. Net. Acceleration. Insert chart. Oh yeah, we have all those 1, 2, 3, 4. Yeah, we have all those outliers here. I believe the outliers are those 2. Let me take a look what we get here. 1.343, right? 1.343. Yeah, that's what you got, 17%. Now let's play a little bit with the outliers. Let's remove them. Should be 0.5. Yeah, 0.5 in the X. Okay, the outliers looks like the outliers are those 2 here. That looks like. So let us plot it. The rest. Insert. Now we get a better curve, right? 119. That I'm getting 119, 1.19. Let's see, 1.19, 4%, right? So the outliers are those 2 data points. So if I were to, if you had performed this experiment, right? I would ask you to repeat those 2 data points that I mentioned, those 2 are here, right? Measurement 2 and measurement 3. Okay, now let me erase that. I want to keep this sheet clean. Okay, 11:35 now. Do we have one more group? We have one more group, right? Group 9, Jade. Did you plot your graph, Jade?
I'm still working on it. All the F nets are 0, so I'm not sure if I'm doing it right.
Okay, so let's do that together. That's group number 9, right? Group number 9 here. Okay, let's see. F net is 0. Well, F net is 0 because you do not have enough decimal places there, okay? So you shouldn't worry about that. Now, let me see. Oh, there's a reason why it's all zeros. Remember, I asked you to fill 9.8 here, right? Okay, the acceleration of gravity. So you gotta put 9.8 here, okay? That's why you are getting zeros here. The net
Okay, got
force,
it.
yeah, the net force is dependent on G. Watch out for that, right? So when you plot F net versus acceleration, okay, you get this nice straight line. And let's see here, 1.13, looks like you get a pretty decent, yeah, 0.2%, okay? 0.2%. Looks like you're doing one of the best data there. Okay, 11:37. Let's see how we're doing here. And do you have any questions?
I have one question, Professor.
Okay, who's that?
It's me, Leiblut,
Okay,
Group
good.
8. Yeah, so when I plot the graph, I will have to take out the 2 outliers.
No,
do-
don't take out the two outliers. Keep them there.
Okay, I will keep them. Okay. Okay.
Yeah,
Thank
we do this exercise so you know, just for future reference for your professional life, okay?
Okay.
I'm not going to label you are group number 8, okay. Someone talking? Okay, let's see. Blessing, are you there, Blessing? Blessing has been there, but is not answering. Okay, Blessing, I'm gonna put another question mark here. Who else? Justena. Justena not here. Justena was initially, then she disappeared. We have 20 here. Blessing. So let me erase that. Someone is speaking. Okay. Okay, so I am going to pause the recording, otherwise this